after I introduce the speaker, and so I can start by introducing the speaker right away. All right, so next up is Christian Ikenmeyer, who will continue on this recent progress in GCT.
Thank you very much, and thanks to the organizers for inviting me to talk here. Thanks for the opportunity. It's about recent progress that I made with two of my students in this direction of finding multiplicity obstructions and finding out if there are multiplicity obstructions. So I want to start with a recap. So we've heard this. We've heard about this result number one now a significant number of times in the workshop. But I want to have at least a tiny bit of self-containment in this talk, and not just jump completely about. Right. So let me actually take some time now to say again these problems that we are looking at. So there's the determinant, right, our favorite determinant, and then there's the permanent. And let's have a look at. So we've seen this kind of action before. You get some linear map here. You can think of this as an n squared by n squared matrix, and you can define what should G times that n be. Well, so if this is the identity matrix, and this is just the determinant, but it might, you might move it around. You do base change. Say if G is an invertible matrix, is a base change. But yeah, it gives you some other polynomial here, G dat n. So that kind of definition we've seen several times. So you might ignore the transpose here just for technical purposes, right? So if, in general, if somebody gives you a polynomial here, you get a different polynomial, but by applying some matrix to it. Right, and it's just your old polynomial, but not evaluated at your original point, but evaluated at like G times your point, right? So it gives you a different polynomial, a new polynomial. But then we think of this new polynomial as having, if this was invertible, then it should be the same complexity, right? So that's what we think of. And now we define the set here by applying all matrices. And it turns out that this has a very nice description that is just, you take all determinants of n by n matrices, and the entries are homogeneous linear polynomials. And now this is this orbit here. And for example, that one here, this polynomial here, can be written as a 2 by 2, as a determinant of a 2 by 2 matrix, and the entries are all homogeneous linear. And therefore we say it's in this orbit here. It's in the C 4 by 4 dat 2. And indeed you will find a 4 by 4 matrix that actually gives you this polynomial, right? So you can read it out from these linear forms. You will get a 4 by 4 matrix. Well, I'm not gonna. This is not so important. How this is like. This is a formalities. Is not so quite so important, right? So variance result shows that you can always find some n, so that if you take the permanent and you pad it properly, then you find that it is expressible in this way. So it will lie in this set here. It will be. So this is a homogeneous version of classical variance result. Okay. And so what you usually do, and we will see also why you do it, is that you close the set. So from the perspective of algebraic geometry, if you close it, so taking all the limit points and adding them to your set, now this is an algebraic variety. And you can replace now the set of all n squared by n squared matrices actually by the general linear group. So making this a group orbit closure, and it will have a lot of advantages to look at this set here as a group orbit closure. Yeah, we will see. So we can now define in a very natural way this DC underscore here as for the permanent as the smallest n, such that your padded permanent lies in this group orbit closure. Okay, so now this GCT conjecture that we've heard about several times now, this notion, this is the border determinantal complexity. One way of defining a border determinantal complexity, it grows super polynomially. Okay, and so. The key observation, that was also, Greta was also pointing this out, but this is the key observation that makes this whole thing work, is that your point lies now in this orbit closure if and only if the whole orbit closure is contained in the determinant orbit closure, right? Because an orbit closure is the smallest set that's closed topologically and also closed under the group operation. But this now makes the whole thing going, because now you want to prove lower bounds, or you want to disprove that the point lies in the orbit closure, but you can actually do this by comparing properties of two varieties. So you have a variety on the left-hand side, the right-hand side. You just want to prove that one doesn't lie in the other. We can do this, for example, with a very weak lower bound technique here. Varieties, for example, have a dimension, right? So if you, for example, the dimension on the permanent side exceeds the dimension on the determinant side, you cannot have this sitting inside here, right? And then therefore, this means by definition now, I mean, you use this if and only if here, this point does not lie in here, and this gives you a lower bound on the determinantal, on the border determinantal complexity of the permanent, right? So any way of somehow trying to prove that this does not lie inside. So, so algebraic geometers use more refined, have more refined notions actually. They don't use dimension. So they study the functions that live on these varieties. So that is, and those are called coordinate rings. And the varieties are studied in algebraic geometry by studying the coordinate rings. So what are those rings? So let me define the set that we are working in. Those are just homogeneous degree n polynomials and capital N variables. You can think of capital N as, say, little n squared, and then the determinant is in there. And you think of the determinant as its, say, its coefficient vector as a point in this space, okay? And it lies in there. So there's just some finite dimensional vector space. This is its dimension here. And now we want to look at polynomials on this space. Okay, you're looking at, and we denote it by this one. This is a polynomial. It's a polynomial ring. So this is a polynomial ring. It's homogeneous degree D component. So this will be homogeneous degree D polynomials in this many variables here. So, and yeah, so this is the canonical classical example that you usually use. So if you haven't, yeah, I mean, if you got lost in the other talks that were talking about these things, then this is this will get you back on the track certainly. So just look at poly 2c2. This has a basis of just x squared, x by y squared. And now every polynomial there can be expressed in this nice form, ax squared plus bxy plus cy squared. And now you want to have in these coefficients, so every polynomial here, you think of it as a point as its coefficient vector abc. And now you're looking at polynomials in abc, right? So you'll say degree 2 polynomials in abc as like this basis here, a squared ab ac, b squared bc, c squared. And you're asking for what kind of functions are in here. So for example, there's the discriminant in there. There's b squared minus 4ac is such a polynomial. And its vanishing set is actually interesting. So if b squared minus 4ac is actually 0, then this means that you can take your polynomial. It has a very special property. It means that there will be some coefficients alpha and beta such that your polynomial can be written as a square, can be condensed. So it's a very special form. So if you want to, for example, then disprove that your polynomial has this simple form, right? So you can think of this as a complexity lower bound, right? So you disprove that that your polynomial has this special format. Then you just take your polynomial, you evaluate b squared minus 4ac. If it's non-zero, you get a lower bound on your complexity, right? You disprove that it can be nicely written in this way, in this succinct way. All right, and there is an action of the general linear group on your coordinate ring now. So it's not only that your group moves your points around, it's also that this group action lifts to the function. So if you have some function, for example, you can ask, is my function an invariant, for example, connecting this to invariant theory, right? And then, so this action is defined in exactly in the same way. So your new polynomial evaluated at some point is your old polynomial evaluated at this G transpose point, right? So transpose again just for technical reasons. So now, yeah, so in particular, you can think of invariance, for example. And so what's the coordinate ring now? So if you have some subset here, you can think of this as, say, the determinant orbit, right? Z being the determinant orbit, or the padded permanent orbit, then you can define the coordinate ring of its closure. So as just you're taking all functions and you restrict the domain of definition to this Z bar. Okay, you had a lot of functions and now you're just evaluating them at Z bar. Some of them will now be the same function, right? And in particular, if Y bar, if you find some Y bar that is sitting inside Z bar, note we wanted to actually, we are having two orbit closures, right? We want to compare them. So if there's one of them, Y bar sitting inside Z bar, then this gives a very natural surjection now of these rings. So those are rings, so polynomials where the domain of differentiation is restricted to Z bar, and now you restrict even further to Y bar, right? So this is a surjection of functions. And in a natural way now, your Z bar, the Z bars that we will consider, they will be closed under the action of the general linear group. So and then this in a natural way lifts also actually to these functions. They will have an action, well, exactly this action that we had here. We will also have the action on all these coordinate rings that we will see. So all our coordinate rings that we see, they will have a natural action of the general linear group in all our cases. Okay. And okay, so going back to this, what we actually want to prove, there's this orbit closure. We want to prove that this orbit closure doesn't sit in this orbit closure, right? For permanent doesn't sit in the determinant. So yeah, I mean, we've just seen if it does, then there's a natural restriction here of functions. So functions on that one orbit closure and the other, by just further restricting the domain of definition. And this actually holds also in any finite degree D if you want to. So still degree D function, if you restrict the domain of definition further, is still degree D. And so now you have this group action here on what are finite dimensional vector spaces. So this is actually just a finite dimensional vector space with a group action on it. And this one is also a finite dimensional vector space with a group action on it. All right, so for example, you could, you could ask, so how many invariants does this contain? Say this might, for example, have SLN squared invariants, right? And this one might also. And you would say you want to count those, right? And so this decomposition that I wrote here is the decomposition into irreducibles, and this is a more refined way. It's just not only counting invariants; it's counting all kinds of different types of irreducible representations. So they're not only invariants; they are also all kinds of other irreducibles, and they are all indexed by some lambdas here. And these lambdas are these partitions, these Young diagrams, right? And and some of them might appear more often. So I mean, it's not clear that there's a unique invariant. There could be several invariants, for example, in here. So this is what is called the multiplicity of lambda in this homogeneous degree D component of this coordinate ring. Okay, and you get this in exactly the same way. You get multiplicities of these coordinate rings in exactly the same way. So one of those multiplicities, for example, is the dimension of the invariant space. And the nice property is now that if you have such an inclusion here, then for every lambda, you will have that the multiplicity on the determinant side is at least the multiplicity on the permanent side. Okay? And so in a sense, it measures size of your orbit closures, right? And therefore, now if you find some lambda where the multiplicity on the determinant side is strictly less than the one on the permanent side, that gives you a lower bound on the determinantal complexity of the permanent. And this is called a multiplicity obstruction. And if you find, this being 0 on the determinant side, then this is called an occurrence obstruction. Yeah, okay. Yes, sure. I should go ahead. I mean, yeah.
If you don't have multiplicity obstruction, can you say that there exists such a mapping? Does it mean that orbit of permanent is included in the orbit of determinant?
No. This is a no. If there are no obstructions, you cannot. At this point, we don't know how to conclude, right? So we would like to have a theorem that tells us that separation can always be achieved with these kinds of obstructions, where we know that that's false in generality, right? So we need, but it might be true in some. If you have additional properties on your points, things like this might be true.
Can you explain what we mean that it's false in generality?
Yeah, I mean, you can take, for example, if you take two generic points, then they will have the same. They will have the same coordinate ring.
But we'll have also the same.
No, they will not have. They will not.
But we'll have isomorphic. Okay, so.
They will have isomorphic coordinate rings. Yeah. So you want to have something. You want to have some. You want to use some special properties of your points to have a hope that this works. And usually, what we think should be a good property is that that the points are characterized by their symmetries, by their stabilizers. And you will see maybe where this intuition comes from, that we want to have these properties. There are no counterexamples known in a setting where these points are actually characterized by their stabilizers. So something like this might be true. Okay, there are no occurrence obstructions for in this. There are no occurrence obstructions for determinant versus permanent, right? So the proof relies heavily on the padding of the permanent, and one can replace the determinant by the homogeneous iterated matrix multiplication to avoid this. And I spent quite a significant amount of time in the bootcamp talk to talk about this, right? So you just watch on those lectures, and I explain exactly the model of computation. It's homogeneous and it's beautiful and nice. Yes.
So sorry, in your previous slide you had this notation poly and Cn.
Yes.
Right. So how does that fit with the example of GLN square det n?
This is So here your GLN. So this is an n squared, and GLN det n sits inside poly n Cn squared. It's a subvariety here. Poly NCN is you can think of Poly NCN as the ambient space where everything lives, and dead n is your point. GLN squared dead n is your orbit. And it sits as a subset of Poly N C capital N. Okay?
So,
That's
so
where
big
everything.
N is n squared.
Capital N, here you can think of capital N as n squared now. Because here you also have a GL capital N, and on the next slide you have a GL little n squared. Yeah. All right? It's good? All right, and so summary is you can, if you can compare these two multiplicities and you get a lower bound. Occurrence obstruction is even stronger. There are no such occurrence obstructions, and the proof relies on padding, right? So that's the summary of part 1. And I want to tell you that something about a good news, that there are actually group varieties you can cook up that cannot be separated with occurrence obstructions, but you can actually separate them with multiplicity obstructions, right? And this is joint work with my student Julian Dörfler and Greta Panova. And this is also a setting without any padding, okay? But it's a toy setting. I mean, this is not even the toy setting that we were talking about outside so far. This is not like Warring Rank. This is the toy setting of toy settings here. But anyway, and even there you cannot have occurrence obstructions. So therefore it shows a significant weakness of occurrence obstructions. So the two varieties are the following. You take what is called the Chow variety sometimes, and it's just if your polynomial can be written as a product of homogeneous linear forms, then it's in the Chow variety. Okay. This is already closed, so I didn't draw the closure here. And so now I switched here the group. The group is not GL little m. Okay, it's not GL capital N anymore. It's like little m now. And the second variety is the variety of border Warring rank at most k polynomials. It's just you have your polynomials and then can be written as a sum of k many nth powers of homogeneous linear forms. And those are your two varieties.
Border Warring rank is supposed to be the powerful set.
So the powerful set. So you want to show that that you cannot. It's called factorizing power sums. So that you want to show that you cannot embed this set here. So this is, of course, this is why I said toy setting of toy setting, because obviously, I mean, it's widely known that if for any reasonable set of parameters, if you have a power sum, it's not, you can't factorize it. Right? It's not a product of homogeneous linear forms. But you can prove it actually with multiplicity obstructions, okay? So and it's not so obvious that you can, right? And so we don't know much about these objects. So you pick any reasonable setting, M and M, and you fix k and d to be n plus 1. And this is an explicit lambda. It's n squared minus 2, n2. Right? It's an explicit construction of an obstruction. Then you actually have an inequality of multiplicities here. And this shows that you cannot embed this one variety in the other. And of course, you can show this with other means. It's not very difficult. But okay. But we can also show that, not in all cases, but we can show that in a finite case, we can set this up and do computer calculations and actually prove that here there are no occurrence obstructions in this setting. Right? You fix your parameters. It's the same setup. Here you got a 7, here you got an 8, so you can actually separate these two. But for all mu, whenever this is positive on this side, this will also be positive. There are no occurrence obstructions. Even in this very simple, I mean, this is a very low dimensional thing. And even here, for this very small setup, there are no occurrence obstructions. And this was a significant computer calculation, so it actually required us to implement new algorithms for, I'll show you in a second. Okay, let me show you. How do we prove that there are no, I mean, this is now a finite setup, right? And I'd like to generalize this, but we don't know exactly yet how to do it. But we want to show if some mu occurs in this coordinate ring here. This is actually a bit more general statement. So this says if some mu occurs at all in the coordinate ring of the ambient space, then already your mu occurs in the coordinate ring of the Chow variety. So this is a bit of a more powerful statement that we have here. And we make use now of the semigroup properties that you've seen now in at least 2 talks. So, and they hold in very high generality, so they also hold in our setup here. So your mu's, remember your mu's that we have here, this is GL3 just. So it's just 3 numbers here, and mu1 is greater or equal to mu2 is greater or equal to mu3, okay? And you take, so the semigroup properties say, you take 2 partitions, and if they both occur in the coordinate ring, then their sum, which is just the component-wise summation of the two, also is in the coordinate ring. And it doesn't work only for this coordinate ring, also works for that coordinate ring. Same setup, right? It says, in other words, in more fancy words, it says the mu's that occur in the coordinate ring and the mu's that occur in this coordinate ring, those are semigroups. Okay, this is what it says. And now how would you show that if whenever a mu occurs in this ring, then it also occurs in that ring? So what we do is we compute. We compute all the 89 generators that actually happen to be in this semigroup. So this means whenever you have anything that happens to be here, then it's a sum, a finite sum of these generators here, a finite sum of these partitions. And then for each generator, we actually showed that they will actually occur. So an irreducible actually occurs in this coordinate ring. We did this with a significant computer calculation. So we actually had to redo, basically, this is a new algorithmic approach to these occurrences here. But anyway, this is not so important. But yeah, and it shows this result, okay? It shows that there are no occurrence obstructions here. You cannot have any occurrence obstructions.
Say programming sometimes helps for theory.
Yes, no, certainly. I mean, this is, yeah, you should, I mean, if you have conjectures, you should back them up, right? So, okay, so, and here multiplicity, yes?
Do you have any intuition why this should be true? You just try variety by...
No, I did have intuitions why this is true. Yeah, I mean, I've been working on these things for quite some time. Yes. Okay, so also this particular one here is not just anything. So this is something that comes, this is one type of so-called Brill's equations for the Chow variety is one of the types that occurs there. And it's the one that's closest to the things that are two-row, right? And then so it gets easiest to analyze it. Okay, so yeah, how would you now show, I mean, so there are no occurrence obstructions, but we do want to have multiplicity obstructions. So how do you do something like that? So and this is a setup that works also in higher generality. So it's not actually limited to just these two varieties. So it works in higher generality. But here we could actually push it to the end, right? So we want to show that this is less than that. And so the proof works. So first of all, you want to have some lower bound on this multiplicity and some upper bound on that one here. So so for this lower bound on that one here, we show that in this specific setup, it's the maximal multiplicity that you could possibly hope for. And then we show that this one is not maximally large. So what do I mean by maximally large? There's in Greta's talk already, this coefficient appeared as the plathism coefficient, which is the multiplicity that arises if you take the coordinate ring of the whole ambient space, right? So this means that all your multiplicities, this one here and also that one, they are upper bounded always by this A lambda dn. This is an upper bound. You can never go beyond that. Because these two are, yeah, those are subvarieties of your ambient space. You can never go beyond. Yes?
Do you have a gap between these multiplicities, or it's just by one?
So here, this would be exactly, here as you see, this will be exactly A. And here we don't know, but the gap is at least 1. So you'll see. The gap is at least...
No chance that we'll have like, say, really large gap.
No, I'm not saying that. There's a well, I'm not ruling out a large gap. I'm not ruling out that there might be a large gap. I do not determine this. I do only determine an upper bound for this. Okay?
Because if there are large gap, it also shows lower bounds for sums of Chow varieties. So for depth-free circuits, essentially.
Okay. Well, let's discuss this afterwards.
Can
Okay.
you remind?
If you change lambda.
Yeah, it's a bit different. Yes.
Trouble with the notation. So Pau n mk. So
That's
n is the degree and m is the number of
Variables, and k is the number of summons that you have. It's k many summons of homogeneous linear forms.
K many summons.
Yeah. And you take them.
M variables.
M variables. Yes. That's that variety. Yes. Here's no k because it's just one summand. It's just one monomial basically. It's a plot of homogeneous linear forms, and that one is a summand. Is a sum of k many, and it's the same degree. It's the same number of variables. It's just a sum of powers of homogeneous linear forms. That's okay. And so we proved in the paper, in this 2016 paper that Peter was talking about, that if your k is at least the degree d, then this multiplicity here is actually maxes out. And you can say this in other words, that this set here is a hitting set for all degree at most k polynomials. Yes?
So in this case, is the stronger thing true that this power nmk is equal to poly NCN?
No, it's not. No, it is not equal. No, it is. It depends. So this works only because lambda is of this specific has actually few boxes.
Oh.
That is because the degree of lambda gives you a degree function that cannot distinguish between pow and actually the whole ambient space. So yeah, I mean, it would also be true if you make k very large, then you get the whole ambient space. Then it's still true. But yeah, we don't have to do that. Okay, so what remains to show is that now you have actually, this is not maxed out. Okay, for the Chow variety, you have something that is not maxed out. So how would you do such a thing? So you do it as follows. Okay, so this remains to show. For your Chow variety, this is not maximal. This is our setup. And we use an inheritance theorem. So we connect this, so it's known by some inheritance theorem that this is basically, this multiplicity of this lambda here is the multiplicity of a lambda. But now your group action, this was a GLM action, but you can actually replace this by a proper GLN. And you take the orbit closure of this monomial here. Like in Pascal-Courant's talk, you had this orbit of the GL of x1 up to xn, right? You take its closure. And those are the same multiplicities, so that's known. And now this is an orbit closure problem, and you can actually study it by looking at its orbit. So this is now maybe a bit a misleading notation. But if you take the coordinate ring of an orbit, so the orbit is not closed, then this is interpreted in a different way. So these are actually rational functions that are defined everywhere on your orbit. So in particular, you get all the functions that you had before, but now you might be able, you can actually divide by functions that are defined everywhere on the orbit. So you get an inclusion here of rings. Okay, so you just have, these are not all polynomials. There might be some rational functions in there. And usually there are rational functions in there. So in particular, well, still everything is nice. You have group actions and everything and multiplicities. And you get an upper bound here from that's given by this object. So why on earth would you do this and go through the length of now actually trying to deal with rational functions? Is because there is actually, so this object here and these multiplicities can be nicely described. So this multiplicity here is just the dimension so this is an irreducible, so ignore the star, okay? So this is an irreducible representation of type lambda, and you take H invariance inside there. So H is the stabilizer of the product x1 up to xn. Also Pascal-Courant mentioned that already, right? So what is the stabilizer? So you can, so it's this group, and you have this irreducible, and we know exactly how these irreducibles look like. It's an irreducible GLN representation of a specific type lambda, and you're just asking what is the dimension of the H invariant space? And so in a lot of cases, this can be actually answered. Right? And in this case here, this is actually a plathism coefficient. So we are just very, very lucky in this case that we have an answer here. Note though, that this is a different plathism coefficient than that one because the D and the N is subtly exchanged the order, okay? It's a complete miracle that this appears here, but so the proof of this fact here is a very general proof using algebraic Peter-Weyl theorem. So this is geometric invariant theory. Algebraic Peter-Weyl theorem shows you that you can actually get such a nice description of this multiplicity. And now, once we have established this fact here, we can actually say, okay, let's have a look at this lambda, the specific one, and let's compare this this big ambient multiplicity here with the one that's our upper bound, right? And indeed, there we can actually prove a gap of 1 here. Okay, and this is a proof based on symmetric functions. So you actually completely remove the whole geometry from there, and this is completely based on symmetric functions, sure functions and things like this. And yeah, so this now gives the desired bound, right? So you have your multiplicity in the Chow variety is the same as in the orbit closure, gives you this upper bound here. This can be nicely described as just this plathism coefficient, which is actually indeed less than the other plathism coefficient, and this separates it. All right. So summary is that, so you have actually an inequality, so therefore you separate these two varieties. And the proof is based on a relationship between the orbit and the orbit closure, right? So there's this inequality here, so you have this upper bound, this interesting one. And in the finite case, we verified that, you cannot do this actually with occurrence obstructions, but multiplicity obstructions work. So now, having such an upper bound is, of course, is a nice thing, and sometimes gives you something interesting, but we do want to connect these two objects close. So in particular, there's a lower bound missing here. I mean, so the upper bound is just not is not good enough. I mean, if you want to, you have these two multiplicities in this cornering of orbit closures. So for one you need an upper bound, for the other one you need a lower bound. Right? This is not. It doesn't give a lower bound. So remember, the lower bound we just got because this was just a full multiplicity. Right? So therefore, we need, maybe some more sophisticated thing here will give us some more insights into what are exactly these multiplicities in the coordinate rings of orbit closures. So, and this is the work with my student Umangatan Kandasamy, where we try to connect the orbits with their closures as close as we can possibly try to connect them. And so it starts with work with Peter about connection of the orbits and orbit closures. So it's a paper called Fundamental Invariance of Orbit Closures. So you start by taking, we're looking at a different variety now. That's because in this variety it actually works nicely. So let's look at the variety x1. So you look at the orbit closure of just this power sum here, right? I wrote this out just so that everybody's again on the same page. What are these varieties? So this orbit closure here, and you take an invariant here, an SLM invariant here on this variety. Okay. And in particular, since this thing exists, this means that this is not in the null cone, right? This is actually, the point is actually stable and things like this. Anyway, you take this phi, and it turns out that this function here, this invariant, is non-zero everywhere on the orbit. It actually follows directly from its invariance, actually. It's non-zero everywhere on the orbit, but if we study it further and we look, where does it vanish? If we look, so you have the whole orbit closure, it's non-zero everywhere on the orbit, but it turns out that it vanishes on the boundary. So it exactly on all those points in the boundary. I mean, outside of that, we just don't really care, right? So it's just we're looking at the closure, and inside the closure, there's the orbit, and the vanishing set of our invariant is exactly the boundary. And yeah, so proof uses Hilbert-Mumford criterion, and as a result, we get that these two rings are actually much closer related than we had on the previous slide. This ring is actually just a localization of that ring. So what does that mean? So you take this invariant, and now you take this ring here, and this element from the ring, and you are allowed to divide by arbitrary powers of this invariant, and you will end up with this ring here. So this is the only thing. So so remember, these were all rational functions, but actually the denominators are all just powers of phi here. And this connects it very closely. So this is a corollary of this fact, immediate corollary. So whenever you have some degree D function here, then you can multiply it by some power of your invariant. This is this map gamma here, multiplying it with some power, and make it actually a proper function in the coordinate ring of the closure. Make it actually come from a polynomial. Looks like a polynomial now. And this inclusion here is just your usual inclusion that we have seen before, right? So this is just sitting inside here because you have rational functions on that. So there is this gamma here, and now we are interested in the question. So what kind of power do you need actually to make this work? And so the theorem is that this for the power sum, and we don't know anything about anything else at this point. But for the power sum, this is really, really small. So if somebody gives you a function here, then the required exponent is just m plus 4d over n, which is really, really, really small, and connects basically squeezes this object here from the left and from the right. And and let me maybe show you, give you an idea of how one could even prove such a thing. That this is so close. Okay, so this is a restatement of the two things. Okay, so how would we go and prove such a thing? So we have actually construction principles that give us elements in these coordinate rings here, in this one or on that one, and actually, and they work with Young tableaus. So you're starting with a Young tableau, and and there's a procedure coming from representation theory that constructs you a function here in this coordinate ring. So it's a pretty limited procedure. So you might end up, for example, with a zero polynomial, and you might not even know that you do this. And so it's very hard to figure out what is happening during this construction process. But but we know that all highest weight functions. So I didn't define what it is, but ignore highest weight functions. You can also think of like all functions can be constructed in this way, right? But we just, in particular, we don't know of, we can't infer much. But what we can do is we have some way of evaluating these functions at specific points. This uses
FT is the highest weight vector.
the FT is the highest weight vector, yes. So you can explicitly construct these FT and that's the highest weight vector. So this has appeared actually in several of our publications so far. It's a construction process from Young tableaus to highest weight vectors, yes. And there's a combinatorial, uses combinatorics and some little multilinear algebra to evaluate at specific points. So it might, but we don't know. I mean, we don't know much. We can't infer much from this, but there's a similar situation here for the coordinate ring of the orbit. And that is not very surprising. So if you have given a Young tableau and that's now called S, you can explicitly construct now also, this will also, Fs will be a highest weight function in this coordinate ring of the orbit. And why is this not surprising? Because these objects here, where you take the H invariants, are actually given already by Young tableaus, right? So this is not a very surprising construction that something like this is there. And also in this case, in the same way, all highest weight functions can be constructed in exactly this way, coming from these Young tableaus. And there's also, we have a similar, not exactly the same, but a similar combinatorial linear algebra way of evaluating at points. So this holds not only for this specific point here of the power sum, but this holds actually in higher generality. But for the power sum, these two ways of evaluating at points are very, very close to each other. They seem like almost being the same. And therefore, we can actually take a tableau S and we construct from that a slightly larger tableau T, such that these two things here that we get are, they coincide on the whole SL orbit. Right, so this means that, so given a function here, it somehow comes from some tableau S. Right, and then you construct now a slightly larger tableau T in here, but the function will on the whole SL orbit will be exactly the same. So the only difference is like multiplying by a power here, and the slightly larger tableau T means so from this difference of sizes of the tableaus, you can read up how large this exponent actually is. This is a representation theoretic property. Okay, and I don't want to go into the. It boils down to a completely combinatorial construction based on tableaus in the end. Okay, and we don't know how to do this at the moment for other varieties, but for this one it works really nicely because these two things are very closely related. I mean, this evaluation and this evaluation algorithm here, they look amazingly close. Okay, so yes.
Does this result have some implications on a relationship between border rank of Waring rank and Waring rank?
Not so far. Does not have, at the moment, does not have a connection. Okay, so summary of this part is that so the representation theory here of an orbit can usually, in most of the cases, much better understood than the representation theory of the coordinate ring of the orbit closure, right? Because here you usually have some formulas. So actually in all cases that we're interested in, we have formulas for these multiplicities here. And in many cases of interest, actually in the cases that we are interested in, these two rings are connected by one fundamental invariant here. And in some cases we understand it better. In some cases it's harder to understand this fundamental invariant. This is actually related. This is related to this that was mentioned. I mean, so Peter mentioned this, and it was the quantum permanent. I think people called it quantum permanent in one talk. Anyway, so this is sometimes a well-known function, but it also has in many cases we have difficulties understanding this invariant. So in the case of power sums, though, the connection is very, very, very close. And the hope is, there is hope, I mean, you might share it or not, that these are closely related in more involved cases than just the power sum. We just don't know yet exactly how close. All right, so maybe the last thing I should mention is that there is, there's one more interesting insight where hope for multiplicities actually could come from. And this is a paper by Larson and Pink from 1990, and it's not so often mentioned when talking about GCT. So if you take so GLN is acting, and you take H being, say, the stabilizer of your point. Let me just remind you, these multiplicities are given just by the dimensions of the H invariance in these irreducibles. And so Larsen and Pink studied not actually these coordinate rings of orbits, but they were interested in studying what are H invariants of irreducibles. And they studied in high generality, so you take H being a subgroup of GLN, but yeah, so they need some assumptions actually, so it should be connected, for example. But under reasonable assumptions, now your group H is determined up to group isomorphism by all these dimensions. So if you know all dimensions, then you get H back. And that's amazing. So this means that if you know all these multiplicities here in your coordinate ring, you actually get H back. And now if you are in a setting where H is a stabilizer of a point that's characterized by its stabilizer, then you actually get that point back, right? So, well, there are some caveats here, but that's the general idea, right? So for example, if you are studying orbit closures of these objects here, like determinant, permanent, algebraic matrix multiplication, or power sum, or the monomial, or matrix multiplication tensor, or unit tensor, they are all characterized by their stabilizer. So this means that if you know all the dimensions here for these objects, then all these multiplicities will characterize your object, right? So, and the conclusion is that, and that is very, very, very vague conclusion here, that a strengthening of the theorem, because that's definitely necessary. The theorem doesn't give you anything at this point, but a strengthening could maybe yield that your point is actually characterized by its multiplicities, right? So, and then that would be a hope towards showing that then you can actually use, then you might be able to show that in these situations here, that multiplicities can always give you all lower bounds that there are. So that's, I mean, but this is very vague at this point. But this is where hope comes from, right?
So why are you saying strengthening? Yeah.
Because there are some issues here. So first of all, there are reasonable assumptions, and then this is up to group isomorphism, which is also not. These are not characterized by its stabilizer up to group isomorphism.
Connected and semi-simple.
Yeah, it's also semi-simple. Yeah, it's connected, semi-simple.
I think that's all. I believe.
It is. Yeah, that is true, but this is not the case here.
Yeah.
Also, I should comment that though this was not mentioned in GCT, this was the result which motivated me for the multiplicity obstruction.
Yes.
Didn't put it into the references.
It's not. Yes, that's unfortunate that it's not in the references.
To the rest of the world.
Yeah, it was hidden, but now it's not hidden anymore, right? So this needs a tiny bit of a strengthening. Well, I mean, it might not be tiny. It's always things are always subtle in these business, right? So
it's a remarkable result.
It is a remarkable result. That is for sure. Okay, that is for sure. So and yeah, so we hope. I mean, there's this hope that one can maybe push in this direction and maybe actually get some result on the lines that, under certain situations, multiplicity obstructions are guaranteed to give you separations if there are separations. But this is a very, I mean, that might be true, might not be true, right? All right. So let me just summarize what I told you, because it was some long time ago. All right. So we. In the computational models that have padding, then we don't have occurrence obstructions that prove strong lower bounds. The padding can be removed. But even if you remove the padding, even in very small explicit unpadded cases, you have situations where multiplicity obstructions can be proved to be stronger, strictly stronger than occurrence obstructions, where you can separate with one and not the other. So one should probably go to multiplicity obstructions. And then, so multiplicities in the orbit are easier to study. They come with a lot of algebraic combinatorics that could be understood. And so the connection to the multiplicities in the orbit closure is hopefully close, right? And it works actually for power sums. It's pretty close for power sums. And Larsen and Pink, this paper then gives hope that multiplicity obstructions could actually work in the end. Right, that's it.
Can you say about this larger tableau when you were relating with phi to the
Yes, sure. I mean, sure, yeah. I can also, yeah, sure. I can tell you everything about this. Yeah. So there's a tableau T. I mean, you know the tableau T construction, and there's a tableau S construction. So. So there's a, so you look at these and you look at the H invariance, right? So V lambda is already given by tableaus. And you just look at the H invariance, which in this case here means that, so lambda has at most m rows, and then the H invariance means that all numbers appear a multiple of n many times, right? And then, and then you want to have it being a linear combination so that the symmetric group actually, that is invariant under the symmetric group. And those kind of tableaus you look at, and those are not exactly the tableaus that happen to be here, but you can, I can show you the explicit construction. You can, it's a combinatorial construction where you try to simulate the behavior here of this invariant. So by splitting it up, actually by splitting this tableau up. So there are the numbers in this tableau, there are too many numbers. So for example, each number might appear more often than it should appear in T. So you have to split it up, and to simulate actually the behavior of what happens in S. In S, things in S might happen that could not actually happen in T, but you can actually, so you can use blocks. You can put blocks in front of S that will actually end up that at the evaluation you will get exactly. So if you evaluate T, you get exactly what S should do.
So the shape is just adding some rectangle.
The shape is exactly, you take the old tableau, you add a long rectangle that has a full number of rows. Okay. And you add it in an interesting way so that it will actually simulate the old thing, yes.
So yes. Maybe Marcus can come up here and start setting up while one final question. I'll go for Milton. Okay.
I can ask him in private.
You should ask him. Yeah.
My question was that you said that some new algorithms were developed by doing that large computation.
Yes.
What exactly?
Okay, so the old algorithm would be would do a depth first search on a lot of different tableaus, and the new algorithm is using a sophisticated caching mechanism. So which my student Julian Dörfler developed by having, so he understood what the original algorithm did, and in this specific case of the child variety, a very specific caching mechanism can be used to speed this up.
Algorithm for what?
For evaluating a highest weight vector at a point on the child variety. So if you have the child variety, a product of homogeneous linear forms, if you want to evaluate at that, on a point on that variety, then there are non-trivial algorithms that evaluate faster by using a lot of space, actually a lot of disk space. They evaluate much faster than you would usually do this on a different varieties. Yeah, but basically it comes at the cost of a lot of storage space. And before we didn't have any we didn't use any storage space. And he cleverly says that let's just use these gigabytes of storage space, and then this is much faster.
All right, so let's thank Christian again.